High performance and durability of a generator set compression ignition engine using synthetic petroleum-based fuels for military application. And abstract, long-term performance durability evaluation compression ignition engine for the diesel-powered generator using ultra-low sulfur diesel, synthetic paraffinic kerosene or SPK S8 fuels have been investigated under the military specification break specific fuel consumption to be around 380 thousandths to 13 plus or minus 13 thousandths and 267 thousandths plus or minus 19 thousandths kilograms kilowatt an hour. Ultra low sulfur diesel and synthetic paraffinic kerosene, respectively, correspond brake thermal efficiency were 287 thousandths plus or minus 2 thousandths and 326 thousandths plus or minus 6 thousandths. Degraduation of the engine performance engine part was not observed during these test periods. Analyzing lubricating oil suggests negligible engine part wear. Frequency power output of the generator, however, not stable with the S8 as well as the ultra-low sulfur diesel. These power frequency instabilities can be attributed to higher volatility, lower density, viscosity of the S8 synthetic paraffinic kerosene, all of which affect fuel injection characteristics. Unclassified distribution approved for public release. Report document. This is 2009 type journal article. Dates covered. Title: Performance Durability Generator Sets Compression Ignition Engine Synthetic Petroleum Based Fuels of Military Applications. Author: Capelli, Wadham, Smith Ridge, Nicholas Johnson, Mark and Winstock Gallant, Sindog Vang, and Eric Sotler. Performing organizations: Department of Chemical Engineering, Material Science, Wayne State University, 5050 Anthony Wayne Drive, Detroit, Michigan, 48202. Performing organization part and report number 244. Sponsoring monitoring agency number address U.S. Army Terror Deck 60 TARS DEC 6501 East 11th Mile Road Bridge 200A Warren, Michigan 483975000. Sponsoring monitor acronym TARDEC. Sponsoring monitoring report number 240. Approved disability distribution availability statement approved for public release distribution on limited supplementary notes submitted to Apply Energy Journal. The abstract: long-term performance durability evaluation compression ignition engine for the diesel-powered generator using ultra-low sulfur synthetic paraffinic kerosene have been investigated under military specification break specific fuel consumption. 318 thousandths plus or minus 13,000, 267 thousandths plus or minus 19,000 kilowatt an hour ultra low sulfur diesel and synthetic paraffinic kerosene, respectively, corresponding brake thermal efficiencies were 280,000 plus or minus 2,000 or 326,000 plus or minus 6,000. Degradation engine performance of the engine part wear were not observed during this test period. Analyzing lubricating oil suggests negligible engine part wear. Frequency power output of the generator, however, was not stable to the S8 as well as the ultra-low sulfur diesel. These power frequencies instabilities are attributed to the higher volatility, lower density, viscosity S8, all of which affect the fuel injection characteristics. And this has been unclassified, abstract, unclassified. This page unclassified, limitation, abstract, public release. Number of pages 27. Introduction: higher efficiency, durability, improve the fuel economy. 1 and 2 with compression ignition engines, making them very attractive for the U.S. military equivalent of the battlefield with the generators to aircraft carriers. Also, U.S. military has implemented single fuel forward, single fuel battlefield policy 3 and 4. This means all the equipment of the battlefield, generators, heavy trucks, and aircrafts must be capable of using same fuel, single fuel forward policy. Requires use of jet fuel number, namely JP8, JP5, and Jet A1. The policy does not allow us to use commercially available diesel fuel in battlefield as an alternate, but only when approved with the combat commander. Only when supplying jet fuel is not practical with the cost-effective U.S. U.S. military, along with the commercial aviation industry, has embraced an initiative to provide the U.S. engineering energy security that can be enhanced for the domestic production of U.S. alternative jet fuel produced with various domestic resources, each of the coal and biomass, investigation of various fuels such as ultra-low sulfur diesel, synthetic fuels 7 and 8, JP8 and JP5, blending biodiesels 14, 15, and military application necessary to identify required operational performance potential issues. The problematic long-term supply of oil, increasing knowledge, health effects of GPA have recently encountered with the U.S. military to foster develop cleaner fuels such as synthetic paraphenetic kerosene, or SPK, as known as S8. Originally proposed, the alternative to the JP8 S8 is derived from synthetic gas with a Fischer-Tropsch synthetic fuel process. 16. Evaluation of the Fischer-Tropsch fuels such as synthetic paraphenetic kerosene S8, military ground vehicles, aircraft, associated equipment, fuel storage, distribution are needed to assist the ability to meet the desired or required operational performance, to identify potential issues as well as potential benefits with the introduction and use of fuels. The Fischer-Tropsch process has been produced with gas to liquid fuel since 1920. Synthetic S8 with a clean fuel, no sulfurs, aromatics, which are historically been very costly to produce when compared to petroleum fuels. Since mid-1990s, the world's most energy companies have started to develop mining Fischer-Tropsch process that all less expensive to build and operate. Fischer-Tropsch synthetic fuels using this technology should result in the reduced exhaust emissions of military diesel engines, including reduced diesel exhaust, particulated matter. The fuels also demonstrate low lubricancy, which can be improved with the military-approved lubricancy. Improvers. Modern diesel engines are designed for the commercial application. Their base calibrations are based on the use of the diesel fuel, not military fuel. Hence, operating standards engine for the SA with the other alternative fuels might need to lead optimal engine performance. Modern compression ignition engine technology with electronic control units make use of the dual use of the calibration viable. However, the understanding of the fundamental effects of the alternative fuels engine operation is required before control standards can be developed. Given the recent fuel focus for the alternative commercial diesel fuels such as synthetic diesel and biodiesel, correlating fuel properties of various fuels for the engine performance durability with the broadest interest. Paper reports the long-term engine performance and endurance for the compression ignition engine with achieved to generate power utilizing two fuels, namely low sulfur diesel and synthetic fuel. S8, the findings will help with better understand how these fuels form in a compression ignition engineering generally set with design military emergency situation. The report describes synthetic fuel for the compression ignition engines, and most of the report uses synthetic diesel fuel blend with petroleum diesel fuels such as ultra-low sulfur diesel, altered engine calibrations using blended S8 on diesel engine has not been reported. In studies, both fuels will be put the static load endurance, low transition test, engine operating performance such as injection pressure, injection timing, were kept constant on both fuels. At the completion of each of the run, lubricating oil was collected and analyzed to understand effects of each of the fuel engine part wear and oil degradation. 2. Experimental section. Evaluation of fuel properties. 2.1. Ultra-low sulfur was additized with the winter condition. Eliminate the batch of the batch variation. 700 gallons of ultra-low sulfur diesel purchased stored in stainless steel container. 700 gallons fuel of synthetic fuel S8 was provided with the National Automotive Center of the U.S. Army, Warren, Michigan. So S8 was not additized, was received at 600 parts per million. Corresponding inhibitor lubricancy improver was added upon arrival. Several important fuel properties were evaluated using the appropriate ASTM test methods given in Table 1. Testing procedures were conducted according to relevant ASTM test methods. Density of both fuels were measured in function of the temperature, and these correlations were later used in calculating brake-specific fuel consumption. 2.2 Engine performance evaluation. Testing system contained an inline 5-cylinder diesel engine, 3-liter, with a displacement of 3 by 4 by 4 by 1 inch bore stroke conjunction with a 50 kilowatt generator. All external load was coupled to the generator engine set can control loading of the engine with a mechanically governed up unit pump a fuel injection system that was calibrated for diesel number 2 fuel. It was not alternated with the testing intake with a turbocharged aspirated engine with a compression ratio of 9.1 to 1 and no exhaust gas return. The exhaust system had no after treatment. The device must be modified with the incorporate inline stroke meter chamber for occupancy with a smoke density measurement engine instrumented with the 2-flat turbine type flow meters, both supply and return fuel lines. The flow meters were calibrated for each type fuel depending on the viscosity values of the fuel being run. They integrated with resistive thermal detectors (RTDs) and flow meters measure the temperature of the supply return fuel lines using the two flow meters with the help of the temperature density correlation. The basic fuel the basic brake specific fuel consumption was calculated in addition with the two pressure gauges each supply and return fuel lines. Differential pressure gauge across the fuel filter was installed with the exhaust gas, and temperature was also recorded with the K-type thermocouple. Fuel was supplied to the engine by a tank about 200-gallon capacity. A hand pump was used to drain the fuel, and in between the fuel changes, every fuel change, the fuel lines were cleaned, and the engine was left to run for at least 2 hours to stabilize on the new conditions. Generator outputs electrical load with three-phase at 208 volts to 60 hertz, utilizing permanent magnet brushless rotating field. Generator linked up directly to the engine flywheel. Engine clutch generator with the frequency of the generator 600 kilohertz was kept constant with 1800 RPMs for the engine. Load bank electronically loads generator set with a manually selected step load. Load was dissipated with the heat when the internal heat exchanger was controlled. Upper set point prevent overheating of the load bank. Generator power, frequency, voltage, current can be obtained using the data display meter with the load bank. 2-3 data acquisition engine performance parameters. Data was procured with using two methods. Data was recorded manually with a certain time intervals. The analog display panel with a monitoring and generator set, oil pressure, engine cool temperature, engine routine were all monitored utilizing this method. Second method utilized control of the data being input with the two flow meters, two temperature probe pressure gauges for which input with the return lines of the differential pressure gauge across the fuel filter, temperature probe, dimension of the exhaust, temperature of the voltage, power, amperage, frequency. Data of the generator measured for the load bank was recorded with using software with data acquisition frequency of 10 hertz. The data was collected with every 5 seconds at 100 data points was average. The basics brake specification, braking specific fuel consumption in kilograms kilowatt hour, braking thermal density, brake thermal efficiencies were calculated to evaluate engine performance during 240-hour engine testing each fuel. 2-4 testing protocol. Both fuels were tested, same testing matrix induced. Endurance tested totally 240 hours, about 8 hours per day, 60% full capacity, 300 kilowatt load with transient load testing 20, 30, 40 kilowatt, 2 hours runtime was performed. A 240-hour endurance test was conducted under the military guidelines, military standard 705C, method 691D. Startup procedures call for the engine to be started with a no-load run with the engine temperature generator fail with stabilization period of 5 minutes. After the 5 minutes, the load of the 330 kilowatts at 60% is applied with a run for 36 hours. The time taken with the reach of the rated voltage frequency starting with the generator is recorded. Shutdown procedures calls for the 30 kilowatt load to be turned off the run of the engine for the 5 minutes and a load. The final shut of the engine during this procedure. Following parameters are monitored: record fuel supply, return line, flow rates, temperature, exhaust temperature, load bank frequency, power, voltage, amperage, oil pressure, coolant temperature, ambient temperature and pressure, and relative humidity were also recorded. The basic fuel for the ultra-sulfur diesel was run 8 hours after completion of the S8 testing in order to assess any of the performance degradation due to the S8 testing. After endurance of the run, each fuel was completed 240 hours. Transient load analysis was also run with the generator. Some of the same startup shutdown procedures for endurance testing were used, but the load was varied with the three different loads: 20 kilowatt, 30 kilowatt, and 40 kilowatt, 2 hours each. Same parameter endurance performance was recorded with the transit load analysis was repeated 3 times for each fuel. 2.5 Lubricating oil analysis. After each test run was completed with the engine oil filter, fuel filter were trained with a sample of using lubricating oil saved from the testing analyzing purpose. 5 ASTM methods were conducted using lubricating oil with testing with the degradation, variation, physical property, chemical composition. The lubricating oil with the ultra sulfur diesel testing CJ4 low synthetic oil, Wild John Deere plus 50. Trademark 15 watt 15W40 synthetic blend engine oil was used during this S8 testing in accordance with the manufacturer guidelines. For the 5 methods follows the ACSM D445 kinetic viscosity at 40 degrees Celsius and 100 degrees Celsius. ASTM D43790, total base temp number. ASTM 3524, diesel fuel dilution and used lubricating oil. ASTM 5185, free metal analysis. ASTM D1796, suit and solid testing measurements. Most of the testing were exemption-free metal analysis conducted with the ISO 9001-200 in the registered laboratory, Detroit, Michigan. The wear metals analysis testing was conducted in Alto utilizing inductively coupled plasma in accordance with the ASTM D5185. 3. Results in discussion. 3.1. Fuel property analysis. Previously mentioned generator set was tested 2 fuels, ultra-low sulfur diesel synthetic fuel S8. The table of 1 property for the fuels used for the testing of the results consistent with the previously published property for the USL ultra-low sulfur diesel S8. S8 has many properties comparable to the ultra-low sulfur diesel. It also has the limits that is prescribed by the ASTM D975 specification. Diesel fuel should be noted with the wear scar diameter of the S8 with the compression ignition LI additive with a military preference 25017. Is determined by a high frequency replicating rig per ASTM D6079 6080 UMs, which does not meet the lubricating specification engine 40 UM maximum, which is the study requirement of the diesel fuel at 520 UMs. ASTM of 6079 testament of the diesel fuel was not designed for the jet fuel, but this testament was used to evaluate lubricancy with the requirement of the diesel engine with 60 parts per million compression ignition LI was added to reduce the high frequency reciprocating rig wear scar diameter below 450. This is necessary to prevent any of the wear of the fuel injection system. Relatively high cetane number, shorter ignition to the synthetic S8 fuel can be attributed to primarily straight long chain of hydrocarbon, a lack of aromatic components at 100% of the C7 and 18 alkalines, according to the certificate analyst provided by the manufacturer. The cetane number affects the cold start with combustion, noise, exhaust emissions. A fuel with lower cetane number can shift the timing of combustion considerably, especially as high-speed, light load operating conditions. This might lead to the incomplete combustion evaluated emissions. Both the viscosity with the density of the S8 are lower than the ultra-low sulfur diesel with the viscosity with the density of fuel depending on the consumption with the fuel. Ultra-low sulfur diesel relatively high molecular weight with the alpha-lytic hydrocarbons. About 30% aromatic compounds, lower higher viscosity density of the S8, but the diesel engine fuel is usually injected with the combustion chamber of the usual volume base of the metering system, which such systems with fuel with lower density yield lower engine power. The density of the fuel can also have a direct effect with the buildup of the fuel pressure of the injection system with a consequent effect of the dynamic starting fuel injection, compensating the effect of density specific power of the involved with adjusting injection pulse width of the duration. Injection pulse width also depends on fuel lower heating value with the viscosity of fuel after effect performance. Fuel injection pump injection system low viscosity may lead to the increased leakage loss of the pumping elements that must make cause the reduction of the amount of the injected fuel quantity. Because of the fuel, it has an effect of the atomization spray patterns of the fuel injectors, which can strongly affect the performance of the engine. Another important property of the fuel is affect the injection characteristics. Volatility of fuel characterized distillation curve ASTM D86 for boiling point range. In the ASTM D86, the distillation character is generated by noting the temperature creating certain fractions of the fuel is boiled off. For example, the T90 value given in table 1, if the temperature at 90% of the fuel sample is boiled off, high volatile fraction fuel tendency to evaporate before fuel gets into the injector. Complete distillation curves are obtained with the ultra-low sulfur and S8 shown in figure 1. 3.2, the long-term engine performance. 3.2.1, fuel consumption thermal efficiency. Both ultra-low sulfur diesel S8s were tested with the generator set at 240 hours, applied load at 30 kilowatts or 60% fuel load with the time required for rated voltage and frequency generator start and after starting the engine. Method 608 with the military standard 705C was between 9 to 15 cents for the ultra-low sulfur and 6 to 11 in the S8. Depending on the ambient conditions, it should be noted that the ambient temperature during the S8 testing were significantly higher for the ultra-low sulfur diesel testing. Temperature was about below negative 15 degrees Celsius. Engine needed to warm up using block heaters. Proper startup generator since the engine was not equipped with glow plugs. The following equations were used to calculate brake specific fuel consumption and brake thermal efficiency. Very simple. Specific fuel consumption kilogram over the kilowatt hour equals fuel consumption rate kilogram hour divided by power kilowatt. Brake thermal efficiency 3600 over the brake specific fuel consumption kilogram over kilowatt hour times LHV or kilojoules over the kilograms. The voltmetric fuel consumption is measured with the two turbine type fuel flow meters installed with supply return fuel lines, which recalculate with the density of fuel of each temperature. Basic fuel supply and basic specific fuel consumption ratio between the mass and fuel consumption brake effective effort, inversely proportional thermal efficiency for a given fuel thermal efficiency with the ratio between the power output and the energy to introduce through the fuel injection with the later being productive with the injected fuel mass flow rate, lower heating value of the BFC and BTE during typical days run are given in Figure 2A, but the 8 hours continuous testing was performed each day, but the data was collected 5-second intervals. Each data point at Figure 2A contains an average of 100 data points. As shown in Figure 2A, with both the S8 and the ultra-low sulfur diesel had relatively stable BSFCs and brake thermal efficiency values during 8-hour testing. S8 had lower fuel consumption, high thermal efficiency. S8, however, they had very relatively large variation compared to the ultra-low sulfur diesel. Average of brake thermal efficiency S8 with a 326 thousandths with a plus or minus 6 thousandths and is 287 thousandths plus or minus 2,000 for the ultra-low sulfur diesel. The variation in fuel consumption thermal efficiencies can be attributed to properties of S8, but it will be described in detail in later section. The brake specific fuel consumption and brake thermal efficiency generator running with the ultra-low sulfur S8 with the function of the accumulated runtime shown in Figure 2B, but the average brake specific fuel consumption brake thermal efficiency during the 240 hours ultra-low sulfur diesel running at 308 thousandths plus or minus 13 thousandths kilograms per kilowatt hour and 287 thousandths plus or minus 2 thousandths respectively, with the brake thermal efficiency over efficient for the generator. For the engine generator efficiency, according to manufacturers, within 90 to 95%. Consider the brake thermal efficiency engine is about 313,000 and 327,000, typical for the compression ignition engine of the class 1, slightly improved lower fuel consumption, hence the increased brake thermal efficiency was observed with the ultra-low sulfur diesel function of the runtime. For example, the brake-specific fuel consumption average brake thermal efficiency during the first 100 hours was 315 kilowatt an hour, or 277 respectively. Average brake-specific fuel consumption brake thermal efficiency values during the last 100 hours were 309 kilograms over the kilowatt hours and 283 respectively, with a 2% thermal efficiency increase that could be attributed to the condition break-in of the new engine suggests generator performance did not degrade during the specific test period. On the other hand, for the brake specific fuel consumption brake thermal efficiency evaluate during the 240 hours, the S8 runs with the 267 thousandths plus or minus 19,000 kilowatt hour and 327 thousandths plus or minus 6,000 respectively. As shown in Figure 2B, for the lower brake specific fuel consumption and higher brake thermal efficiency compared with the ultra-low sulfur observed with the engine was running at S8. Lower brake specific fuel consumption gravimetric with the S8 with the attributed to lower density with the S8 with compared with the ultra-low sulfur diesel with the table of 1 result with the consistent with the result of the Abu-Drajad sequence with the reported improved fuel consumption with even lower viscosity the GTL 7-8 with lower viscosity result with the increased fuel loss during the injection process. Ultra-low sulfur the high viscosity result with the slower evaluation of the process, thus retarding fuel injection time, normally decreasing fuel consumption. Also, it reported for the given injection pump settings, fuel was higher density increased with the blast flow, is trimmed with slightly decreased with brake thermal efficiency during 240 hours. S8 testing with design can be seen in Figure 2.4. That could be the internal leaking of the S8 with the fuel delivery system, since the S8 had been reported to have compatibility problems with the sealing materials. However, the average brake specific fuel consumption, brake thermal efficiency with the ultra-low sulfur after completion of the S8 run were 296,000 kilograms kilowatt an hour, 299 kilograms kilowatt per an hour, respectively similar with the value of the same initial 240 hours of the ultra-low sulfur diesel. This confirms that there are no permanent damage was done with the engine during the 240 hours of S8 testing based on the ultra-low sulfur data before and after the S8 test. Brake specific fuel consumption, brake thermal efficiency, ultra low sulfur, S8 with the under different engine load conditions given in figure 3 for the S8 lower specific fuel consumption, ultra low sulfur diesel, every level of the engine load, high specific fuel consumption, hence the lower thermal efficiency, both ultra low sulfur diesel S8 were observed with the 20 kilowatt load conditions, highest brake specific fuel consumption difference for the S8 compared to ultra low sulfur diesel, heavily observed with 30 kilowatt loads. Ultra low sulfur diesel 11.7% higher than the S8 with the highest brake thermal efficiency increase between loads were 20 to 30 kilowatts. Both ultra low sulfur diesel at 17.2% and S8 23.6% of the brake thermal efficiency increases 40 kilowatts, 7.8% ultra low sulfur diesel, and the S8 was only 2.3%. 3.322 exhaust gas temperature smoke opacity. Figure 4A shows the exhaust gas temperature of the various engine running time with a typical single day for the engine testing ultra low sulfur diesel for the S8 with 30 kilowatt loads. The ambient temperature for the test shown in Figure 4A with 15 degrees Celsius for S8 and negative 3 degrees Celsius for the ultra low sulfur. The engine exhaust gas temperature recorded each day with the testing show for the equilibrium of the exhaust gas temperature. Independent ambient temperature both varies with the fuel temperature. Type for S8 show with a 50 Celsius higher than the engine gas temperature compared with the ultra low sulfur diesel. This would be due to the more complete combustion of the S8, which consists of the higher of the brake thermal efficiency. Figure 4B presents the engine gas temperature as a function of accumulated engine operating hours. No significant change was observed for the S8, and slightly increase for the engine gas temperature was observed during the 240 hours ultra low sulfur diesel testing. The average smoke capacity was recorded after an hour of the engine running at 13 plus or minus 4% with the ultra low sulfur diesel, 7 plus or minus 3% with the SD. Continuous smoke occupancy measured were not possible, but the inline smoke meter due to the water condensation on the detector. Low smoke opacity with a 7 attributed to several factors: cleaner aromatic sulfuro-free nature of the S8 compared to the ultra low sulfur diesel. B, the lower initial boiling point SD with respect to the ultra low sulfur diesel, which leads to the easier fuel evaporation relative to the low starting temperature, and C, with the lower viscosity 7 and 8, lower temperature with increase the rate of spray atomization. All of these phenomena lead to lower smoke opacity in S8. Alright, generator stability. The military guidelines generate testing with the military standard 7005. See with the list supplement for the test generator stability method 6082A. Describe the long-term frequency voltage stability method 619.2C. With describe the percentage voltage derived with the rated loaded test. Figure 5A to display with the generator power frequency tray for the 8-hour testing when the engine was running with the ultra-low sulfur and the S8, with the major difference observed with the S8 testing compared with the ultra-lower sulfur. Diesel with the frequency power output of the generator not stable with those for the ultra-low sulfur. Diesel S8 with given an average frequency with a 60.27 plus or minus 300.039 hertz, while the ultra low sulfur had 60.18 plus or minus 8,000 hertz. S8 given the average power of 29.59 plus or minus 14 kilowatts, while ultra low sulfur had 29.45 plus or minus 400 hundredths of the kilowatt at 60% load. Instability power frequency may be due to the fact that the engine calibration parameters such as injection pressure, injection time were optimized ultra low sulfur, but not with the S8. With the S8, which is not volatile, figure 1, ultra low sulfur partially vaporized either in the unit, injection pump, or the line from the injection pump to the injector. Therefore, each injection different amount of fuel, with each slightly higher and lower, causing engine to oscillate. Speed, frequency, and low base of the distillation curve is present. Figure 1, initial boiling point of the S8, but it's about 20 degrees Celsius lower than that of ultra low sulfur diesel. 5% of the S8 boils off at 167 degrees Celsius, 1 atmosphere pressure, compared with the 201 Celsius for the ultra-low sulfur diesel. Another possible explanation attributed to the lower density of the S8 under some load conditions. The engine requires higher mass flow of the lower density S8 compared to the ultra-low sulfur diesel. This instability can be a combination of higher volatility, lower density of the S8. This should not be noted, but no physical damage injectors were observed after the S8 testing, showing there were no cavitation of S8 vapors side injectors. These proper power frequency variations did not damage any part of the fuel injections to ultra-low sulfur diesel testing. Just after 240 hours, the S8 testing did not show any instability. Generator power frequency of the ultra-low sulfur and S8 run at a function of the accumulated engine runtime presented with the figure 5b. As can be seen in figure, both the frequency is more stable with the ultra-low sulfur diesel through about 240 hours of test compared to S8 testing. Day-to-day variation both generator power and frequency of the larger S8 compared with the ultra-low sulfur diesel. The varying frequency power over the functional of the engine runtime are different with the 40, 30, and 10 kilowatt load conditions given in the figure 6. As shown in figure 6a, oscillation frequency power is greatest when the generator is fueled with the SA at the high load. 40 kilowatt load generator produces an average frequency of 60.33 Hz with a minimum maximum frequency of 59.07 to 61.59 Hz respectively. These values are closer to acceptable range of 58 to 62 Hz as specified by the U.S. Army 60 kilowatt tactical quiet generator set with the mass flow rate effective due to the difference density of the greater the higher loads. On the other hand, frequency power trace of the ultra low sulfur remains stable with the different load conditions. Figure 5b. The currents A in terminal A, B, and C with the voltage V across terminals A and B and C and C at A. Typical 250 minutes for the engine runtime presented with figure 7 under steady 30 kilowatt load generator produced 82.3 current average and 205.4 volt ultra low sulfur diesel. Figure 7a. While 7a produced average current of the 82.44 amps, average voltage of 206.69 volts. Initial spike of the current three terminals were observed with the load change for the no load with the 80 kilowatt load. The ultra low sulfur diesel voltage stabilized instantaneously after initial voltage dropped down load over to 30 kilowatt load. However, took longer than the S8 to stabilize the voltage related to value with no load 30 kilowatt load. Percent voltage drop measured according to the method 619.2c. Both the ultra low sulfur and S8 from no load with 30 kilowatt load is less than 400ths over the percent of the generator performance parameters. Performance voltage drop frequency voltage stability is within the limits of the military specification, but they approach out with a specified range. S8 is utilized with the higher load conditions. 5. Use lubricating oil analysis. The viscosity of the total base number of the diesel fuel dilution soil testing with both sets for you with the various fresh lubricating oil presented in the table 2. Lubricating oil, you with the ultra low sulfur testing the CJ4 lowest synthetic oil with John Deere plus 550 watt W40 synthetic blend used for the S8 testing accounts for the difference of the base oil properties. No major deterioration viscosity of the total base number of the fuel percentage or suit, but the percentage was observed with either fuel. Less than 1% of the oil dilutions were observed both with the ultra-low sulfur diesel and S8. Interestingly, there was a decrease in viscosity of 40 degrees Celsius, 14% decrease in ultra-low sulfur diesel, and versus 5% decrease in 7.8. Contrast reported tendency for the oil and increase the viscosity over the time. A greater decrease over the total base number was observed with the oil used in the 7.8 then used with the ultra-low sulfur diesel. The total base number value was used after the 7.8 testing with the 7.5 ultra-low sulfur diesel 6.8. However, the both values above recommended per replacement levels of 3.0 milligrams KOH grams. Where metal analysis resulted in has been table 3 as with the other test lubricating oils were tested against fresh oil but added within this test freely metal analysis ultra-low sulfur diesel. S8 fuels analysis conducted to see any of the metals present with the fuel present. They used lubricating oil along with and aware of the metals using oil. Major elements interest the aluminum, chromium, nickel, ferrite, iron, zirconium, and cobalt and molybdenum, which are present within many of the engine parts of the piston bearings and crankshaft, gears, compression rings. The most abundant metals with the added package of oil, zinc, and phosphorus, which come from the zinc phosphate, were due to the anti-wear of lubrication as seen in table 3. Only molybdenum, iron, and barium shown significant increase with use in lubricating oils. However, the values 14 parts per million to 19 parts per million are not high enough to consider the possible wear. Those do not seem to be with a significant amount of wear. The major components are as well within the lower bounds of the typical range of all the runs. Alright, 6. Conclusion. The performance generators that are set fuel for the ultra-low sulfur diesel synthetic fuel 7 and 8 was investigated. The better fuel consumption, hence higher thermal efficiency was observed with the S8 using the ultra-low sulfur diesel. Engine performance degradation was not observed during the 240 hours of the ultra-low sulfur diesel S8 testing. Engine part was not observed with either ultra-low sulfur or S8 testing. Instability generator power frequency when using S8 could be a potential problem in the military emergency power generator applications, especially high power demand situations. Data presented here help identify the potential problems with using synthetic fuel, with namely synthetic paraphernatic kerosene and compression ignition engine technologies, auto calibrating capabilities, which can compensate for physical property differences. Various fires should be investigated. Disclaimer: reference herein the specific commercial company, product, and process, service, trademark, trade name, trademark, manufacturer, otherwise do not necessarily constitute the implied with endorsement, recommendation favoring the United States government or the Department of the Army. The opinion of the authors expressed here and do not necessarily state that they reflect the United States government or the Department of the Army shall not be for the advertising, production, and endorsement purposes. Acknowledgement, financial support of the Department of Energy and Michigan 21st Century Job Funds research greatly acknowledged. And then it goes into the references, and then there's more references. Properties of the property lubricating setting, cloud, PowerPoint, carbon residue, LHV, flashpoint, viscosity, distillation, temperature, and density, ASTM method, ultra low sulfur, so SN8. Use lubricating oil in the analysis. Metal, ultra low sulfur, S8, fresh oil, lube, fresh oil, S8, fresh oil, lube, ultra low sulfur, oil, lube, used oil, ultra low, and S8. And then shows all the different metals. Alright, figures shows the distillation curve of ultra low sulfur diesel S8 constructed. Green, ultra low sulfur diesel S8 recovery times and temperature percentages. Alright, we have brake specific fuel S8, brake specific fuel USD, red square, filled in red square, blues. Engine runtime in minutes, brake system fuel class kilograms kilowatt an hour. Engine load kilowatt and brake specific fuel kilowatt an hour. Engine runtime in minutes, exhaust gas temperatures. Engine runtime in hours, engine exhaust gas temperatures. Engine runtime in a minute, generator power kilowatt an hour. Engine runtime hour, generator power kilowatt. Engine runtime minutes, generator power kilowatt frequency, power kilowatt frequency, generator power, engine runtimes. Engine runtime, generator voltage, engine runtime. And that completes basically the performance durability generator set and compression synthetic petroleum based military applications.